Start. So, as I said, sorry. As I said, big annotation is for explain efficiency of algorithm. So when you're writing your algorithm, it can be different time complexity and space complexity. Saying time complexity, I mean how long your algorithm executing. Saying space complexity, I mean how much memory from machine your algorithm will take. Big connotation is really important concept when you're writing programs and when you're designing algorithms, because this can give you understanding how your program will work. And it's important to be able to prove that your solution is efficient. So then better time complexity we have in terms of big annotation for our algorithm, then faster our program performs. Then better memory complexity we have for our algorithm, then less space, then less memory our program will take. It's important on cases when we have a lot of data, a huge number of input, and it's important to optimize our programs if we can do it. First of all, I will bring little more math here. So why it's annotation? Why all these programmers go in this term, annotation? So that's come from math. It's mathematical term. It's from function analysis. And we say that annotation is about function, that it's about we can guarantee that our function will take some values at most with much of other function that we can describe with some constant. In mathematical analysis, it looks like O of g of n means that for function f of n and function g of n exist positive constant and positive number and 0. From that number, we have this postulate that our function is always less than function g of n. So we can guarantee that our function will take these values by y, as you see, it's less than c multiplied on g of n. So example, binary search. We will look at this in this presentation later. So binary search is always O log by log of n. It means that you can guarantee that time complexity of binary search is at least not much, not as much as O log n. I think I already have some questions. Okay, it's about recording. Yes, we have recording of this presentation and some links. I think Helen will put all links right now. Okay, let's go next. What other complexities exist? So if you see here, we said that we have some values that at least here it's less than c of g of n. What about lower border? Yeah, it's also have, in math, we have the theorem omega notation that can give you example that you can provide that function f of n is at least more than function g of n if exists some positive constant, and for this constant from some number n0, for some number n0, we can guarantee that this function f of n more than cg of n. That's called omega notation, and it's about lava bronze. And for example, the same binary search, it's always at least more than, at least no faster than log of n. That's why omega notation for binary search will be log of n. The next, could we describe something like we have bigger border and lower border? And yeah, that's called Tata notation. When you say that f of n is theta of g of n, that means that exist two positive constants. And for these two positive constants, we can say that f of n line between these constants multiplied of on g of n. So, for example, again, binary search, we said that the bigger band is log by n, and the lower band log by n. So for log by n, it's theta notation. It's simple for binary search, but for some algorithms, you can't say that it's only one log n function. For some algorithms, your O complexity will be n quadratic complexity, but omega complexity will be log n. It depends on algorithm. And let's look which complexity exists. By the way, I always say n0, yeah, because it's important that you see this function can perform differently on these small numbers for n. Guess that n, the number of elements, the number of your input. So only for big numbers, these can be true. And that's okay for us. For small numbers, if your input about 10 elements, you do not care about what complexity of algorithm, because it will be fast. It will execute in memory, and it will took really small number of memory. And you can always say that if my input really small, I can go any algorithm. But for big input, it's critical to think about better and optimized algorithms. So, which complexities exist? The worst complexities is logarithmic, exponential, that's not shown here, quadratic, and this is with algorithms easy to design, but it's very bad to use these algorithms for big numbers of input. The next one is linear complexity. It's simple, like you have some input and it's just linearly increasing with the number of inputs. Then more elements you have in input, then bigger your complexity, like for all of them. Quasi-linear, it's when you have it grows faster than linear, because you multiply your n by log n, but it's really better than quadratic. And really good time complexity that we always want to achieve is logarithm. It's always about logarithm by 2. And the next thing is constant complexity. It's very good if we can achieve constant complexity. Let's look more on it. So as I said, here we will start from constant. Constant, it means that it doesn't matter how big your input. The only thing that you know that you have some constant number of steps that you need to do to execute your algorithm. The good example is hash table to retrieve element from hash table. We looked a little bit for hash table in the previous session, and we will look more in next sessions. The other example is when you know that your input depends on only alphabet numbers. For example, we know that our alphabet numbers is from A to Z. Oh, I can draw here. Yeah, finally. And we know that it's only 26 characters. Yeah. And that means that we will do at least 26 steps for our algorithm. And in this case, we have constant. We can say that our algorithm took O by 26 steps. And the same, we can say that it's 26 multiplied by O by n. And in this case, 26 is a constant that I showed in previous slide. So that's why it's O big notation. The next, linear. Linear is simple. The more elements you have, then bigger steps you need to do. And for linear, it means that you have n steps in your algorithm. So for example, in your algorithm, you need to find at least one negative number in the array. So you just go through array element by element and find at least one negative number. If this negative number doesn't exist, you need to look at every element in algorithm in an array, and you need to do n steps. And doesn't matter how big your input, doesn't matter if it's 10 elements, 20 elements, or 30 elements, you always do n steps. In case if it's 10 elements, you do 10 steps. In case if it's 1000 element, you do 1000 steps. So it's linear growth with the amount of the input. The next, quadratic. Quadratic, it's an example of it when you have an array. It's about n elements, and for every element in this array, you need to look at other elements in this array. You need to check all elements again. So you do these steps like twice, and for each element you do n steps. So you have n steps in general and n for each. And as a result, it's n quadratic. Example is a simple approach to find duplicates in the array. So you have an array, you know that somewhere a duplicated number. So you go for first element and you check, is there in this array any more the same the same element as first element. Then you go to second element, and again, starting from first element, you check if there in array at least one duplicated the second element. In this case, you go with n-quadratic complexity, and you can definitely tell if there are some duplicates or no. Exponential complexity. This is big, huge complexity. If I go on previous slide, I should put it here between factorial and n-quadratic. It looks like this. So exponential complexity, it's when you have two more steps at your n step. At every step, you need two more steps. The example is recursive approach to find a member of Fibonacci sequence, and I will show it a little bit later. So I will explain how this exponential complexity is coming. Quasi-linear, as I said, it's very popular for algorithm for sorting. Quicksort, merge sort, you will hear about it in next sessions as well. They have this quasi-linear complexity. So quasi-linear means that on every step, you need to do also log n steps. And the logarithmic. Logarithmic is always, it's about logarithm of power of 2, but we basically just skip this second number. So if I say in more details, it's always logarithm by power of 2. But if you will look in the internet, in the books and etc., you will see just logarithm by n. It means that when you have your algorithm, at every step and the next step, you should do twice less steps. We will look at binary search, so don't worry, I will explain it in more details there. Do we have some questions as far? So I see that no, don't hesitate to put any questions. The next one. Let's start with deeper understanding the algorithm complexity. First of all, Fibonacci sequence. What is Fibonacci sequence for details? This is it's a popular sequence, and it's coming when you know that the member of this sequence you want to compute it, so it's computed on previous result. So 1 and 1, they are default, and the second number is result of 1 plus 1. Then the third member is 1 plus 1. The first number, it's 3, it's 1 plus 2. The fifth number, it's 5. I'll look at this. 5 is 2 plus 3. Then next number, 8, because it's 3 plus 5. Then next number, 13, 5 plus 8, and 21. And you can put in the chat what will be the next number. I will be happy if somebody will put it in the chat. Yeah, 34. Thank you. Thank you, Gary. Yeah, so 34 and etc. So you got the idea. How we can program it? Recursively, it's really easy because you just need to compute two previous members of Fibonacci sequence. So you go to n minus 1 and n minus 2 member. Now let's look how our program will execute it. Okay, so we want to compute the sixth member of Fibonacci sequence. We go to the function with 6, and now we see here that we need 5. We need member 5 and 4. I see that somebody have a microphone, and I hear some cat here. Can we mute? Yeah, thank you. Okay, so we have the sixth member of our. We have to compare the sixth member of our sequence. So the first step, we go and compute the fifth member and fourth member. When we starting to compute fifth member, we need to compute fourth member and third member. When we come to compute fourth member, we need to compute third and 2, and so on. And that means that at each step, we need to do two more steps. And then at each of these 2 steps, we need to do 2 steps again. So our complexity will be 2 for first step, 2 for second step, 2 for third step. I will say steps here. Yeah. So it's third step and etc. And here it's our nth step. And this means that our complexity is 2 in the power of n. Yeah, I hope that it's a good example. Let's go next. Quadratic complexity, that's better than exponential complexity. So we, as I said already, we need to go through array and look at each element for every n element. The example here that we have array of numbers and we want to compute the sum of all remained elements. So for first element, we just summarize 4, 6, 8, and 10. Then we go to second element 4, and we want to compute the sum of 2 plus 6 plus 8 plus 10, and so on. So we pick up some element and we compute the sum for each element. And yeah, so we do n steps for every step. I have the question in the chat. Can you explain exponential complexity once more? Thanks. I have one more person who I want to mute. Okay. Can it mean? I don't know. Thank you, Helen. One more explanation for exponential complexity. Now let's look again. We want to find sixth member of our Fibonacci sequence. So we should do twice computation on this step. And on next step, we should do computation twice again. And this means that for each step, we should do at least 2 steps for computation. So this you can consider like 2 operations, yeah? So you have the step n, and for n step, you need to compute n minus 1 and n minus 2. Then for, it's like, I will try to explain it like step 1. So you need to compute n minus 1 operation plus n minus 2. Then for n minus 1, you need to compute and summarize n minus 2 and n minus 3. And that's mean that you have this operation multiplied by 2 steps for these operations, and then 2 steps for this operation, and so on. And suppose that here you have one more when you want to start here from 7, yeah? If you start here from 7, you have full tree twice bigger, because here you have, sorry, let's suppose that we have 8 here, 8 and 7. Yeah, 7 and 6. And for 7, you again should compute 6 and 5. So it's 6th member of sequence and 5th member of sequence, and so on. And as you see, it's huge, a huge amount of operation that come when you just go, then you little bit increase your n. You little bit increase your n, but your next number of operations is grow exponentially. Okay, I hope that was helpful. Are there well-known algorithm with complexity more than 2 than exponential? No, this complexity is not maximum, because, for example, you want to compute factorial, and you can do it with recursive function. So that will be factorial complexity. I don't know on the top of my head what is using in real life. I hope that in real life it's always optimized somehow by caching, by memory, or something else. Is any recursion going to have exponential complexity? No, not every recursion going to have exponential complexity. With recursion, it's like non-tail recursion. You need to do some more steps for this recursion. But you could, sometimes recursion doesn't mean that you need deeper and do more steps. Sometimes you just need to compute the result and return it. In this case, it will not be exponential. It can be even constant. So recursion doesn't mean, on recursion, you can, on the next step, have only 2 operations and then return, and then go to the next branch of recursion. So the answer is no. Any permutation? Okay, so here we looked at this example, and already here we can optimize it, because if we want to know the sum of remained elements like this, we can just compute all sum. And for every element, we just decrease the sum from each element. That will be linear complexity. So with this example, here for the first time, we go through whole array and we compute the sum. The next iteration, again, we go through whole array and we append with sum to our result, and the result's the same. We do n steps at this point, and then we do n steps at this point, and the result will be 2 multiplied by n steps. And as I said, O notation is about some positive constant that can be applied. And in this case, the 2 is our positive constant. So we can say that this algorithm have linear complexity. Let's go to more example. With this simple example of linear complexity, because we have only once, we go through array only once, so we just go step by step for every element. So we do n steps, and in this example, we return squares of numbers. And one more, find number. We have some items, and again, we have number and we want to return the index, so we just go through array, we just check every number if it's our number that we looking for. If we didn't find it, we return -1. If we found, we return the index. Let me check if we have any questions. Okay. Okay. What if this array sorted before coming to our input? Do we need to go through all elements if we know that it's sorted and we can guess where is the element? Yeah, so let's think about it. We want to find 8 in this array, and we know that it's sorted. If we know that it's sorted, that means we can pick up the middle of array. It's a 6, and we go to the middle. We check if it's more or if it's equal to 8. And we see that it's less than 8. So we need to check only right half of array. Now, suppose we have one more element here, 9. So we again go to the middle of this right half of array. And we see that 9 is bigger than 8. And that means that we should go to this half of remained array, or the left half of remained array. And here we've won here. Or if we found here that, for example, we can look if our array contain the element 7. We see that it's 8, and then we couldn't go anywhere because we already checked 6. And in this case, return -1. And that's approach called binary search. And it's more optimal than linear. Let's look at this picture again. I will give you a chance twice to look at it and see how less steps we can do if we go with binary search. We want to find 37 in sorted array. So again, we look at the middle, 23 is less, so we go to the right, and we're doing it before we will find a good example, find 37 if it exists. How the code will looks like in binary search. So we check first of all, with this recursive algorithm, we check first of all if start more than end, because we will do it every time when we will try to find element. We say that this is the index of middle element, and then we check if our element is equal to middle, then we found it, then we won. If it's less, then we go to the left, and this is from start to middle -1. So we go to left half here. But if it's more, in other case, we go to the right place, and then we do it again. We again check with half of array. Once more again on logarithmic complexity. As I said, we always say just logarithmic, but it means that logarithmic by 2. So we do, at each step, we do twice less. We have to do twice less steps. In other words, this is binary search tree, and we want to find the element that is 27. So we go to the root of this binary search tree, and we see if it's more or less than 27. We see that it's less, then we go to the right. And we know, so on the first step, we wanted to check n elements, but on the second step, we need to check only half of these elements. On the third step, we need to check only twice less elements, and etc. And when we found it, we see that we needed only these steps. That's why it goes with logarithm. Before we go to quasi-linear complexity, do we have any questions? Okay, I see that people helps me here. Don't hesitate to put questions. Good questions. At what point it starts to be a lot of elements? So it depends on the structure of elements. For example, if you have long, that doesn't get too much memory, and the number of elements, then we say that it's huge, is less than if we have strings as our elements. If we have strings, they get really more memory. So for longs number, and it also depends on power of our machine. And to think more about these questions, you need to also think about the memory and the caches, because when you execute your program, it can use 3 layers of cache, and then it goes to operative memory. And the best situation for you if you can just fit in caches. The cache is about several kilobytes, And if your data fit in several kilobytes of array, you can compute what data inside, what structure with data, and you can see that it's fit in all caches. There is L1, L2, and L3. So if you fit in these caches, that's good. You won. You can use any algorithm. If you go to operative memory, that means that it's already big numbers of your input. And that means that you already have to think how to optimize it. And if you have huge data that should go to hard disks, even more than operative memory, so they don't fit in operative memory. It's huge numbers. I hope that I answered the question. So let's look at quasi-linear complexity. So as I said, when we have n elements, we need to do n steps, but for every step, we need to do more log n steps. And a good example to explain how it works is merge sort algorithm. You will meet it again when we will talk about sorting algorithms. And today, let's look for the first time on it. Suppose you have this array and you want to sort it. You could do by something with quadratic approach. Just check every element if it's more than a neighbor, for example, or if it's not in the good place. It's insertion sort and bubble sorts. They are quadratic, they are simple, and they are not optimal because it's quadratic. You want to do something magic for don't compare each element with each element. And the magic here is that, okay, you divide this array for two parts, and then you will work with every part. For every part, left and right, you divide it again. You again have left and right parts. And here, when you have two elements, you think which one is more. And if they are not ordered, you swap it. And you create this part sorted. And the left part is sorted and the right part sorted as well. Now you collect it in one part. And here you do with merge trig. It's called merge sort. So it's because you merge your two parts of arrays here. You look by two pointers at this one and at this one, and you check which one is less. You see 3 is less, so you put it here. Then you compare 27 and 43. You see that 27 is less, so you put it here. Then you compare 38 and 43, so 38 is less, so you put it here, and then you put 43. And then you have this part is sorted. You also have this part that came from other branch. And you do this merge trick again. You compare 3 and 9 and put 3. Then you compare 9 and 27 and put 9. Then you compare 10 and 27 and put 10, and etc. Let's look at code. The code it's about recursive approach again. We have this middle. As we said, we go to the middle of array. We divide it by two parts, left and right. And okay, left, right, it's from start to middle, and right part from middle to the end of array. Yeah, and then we do this merge sort algorithm for every part. And for every part, the mostly that we are doing is dividing algorithm, dividing array, and then we divide it and gradulated it to one element. We starting to compare with elements. Yeah, if it's just one element, we skip dividing parts, and we check which one is more, and we put elements in array. Our result, yeah, we just will fill our arrays at our input, and yeah, we're starting from 0, and we put that which element that is less. And when we collect it with 27 and 38, we return array, and that means that we go to, oh, sorry. And that means that we go here when we have two arrays, so left and right parts together, and they have already more than one element, so we come with our merging algorithm again. And these parts need to fill the remained elements when we check everything. And yeah, and that's all. Do we have any questions so far? Okay. And constant complexity, favorite complexity. The simple example here is hash table. When we want to extract complex by complex keys, we want to extract values. So hash table is about, we have some hash function. We put there our key. The hash function compute from our key a number of bucket, and in this bucket we put the value. So when we want to extract the value by the key, we need to execute our hash function. And we know that hash function takes several steps, but it doesn't depend on how big our input. It's always the same steps here. So that's why that's called constant complexity. Yeah. And let's revisit it. So in this picture, factorial, exponential, quadratic, and even n log n is marked as red because we want something more optimal. Basically, quasi-linear complexity n log n is also quite good. So it's a complexity for sorting algorithms because it's impossible to sort algorithms to sort arrays faster than n log n. It's the most optimal complexities, time complexities, and it's without spending space. Yeah. I didn't mention a lot about space because all my examples, yeah, this example, that space an element when we put an element in our hash table. That's if during your algorithm you create a new, for example, hash table for fast extracting elements or for storing unique elements, that means that you create often space. And be careful here. For merge sort, we didn't create any extra space. Here we also didn't create, so here memory is constant. Yeah, in these cases, memory was constant. And here you can say that you create the memory for n elements. That's why your memory space complexity will be of n. Yeah. So O of n is good complexity. Linear complexity is really acceptable by programs. Logarithmic complexity is really desirable complexity, and constant complexity is like the dream. Yeah, so thank you. Let's check if we have more questions. I see some recommendations of good books and sites. That's cool. Thank you very much. Yeah, so let's switch to quiz. I hope I will not took too much time for now. Well, where is my quiz? Yeah, I'm putting my quiz in the chat. And please follow the link, answer questions, and tell me somehow that you marked it, that you finished it, and we will look at the answers. Yeah.
You enjoyed my cat?
Yes.
Again, using this opportunity to advertise adopting from shelters. This tale is from the most elite dumpsters of Kiev.
Oh. Yeah, if you finished quiz, please put it in the chat somehow. And we are going, let's wait for 2 minutes and let's discuss it. I will show you the answers. Yeah, I see them. Great. Yeah. The link for the quiz in chat. Great. Okay, 1 more minute. Yeah, I see a lot of them. I really enjoyed. Okay, 20 seconds. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1. Okay, so let's look at our questions. Okay, which one is the most common to describe complexity of computer programs with O by N? Yeah. Yeah, remember that omega and theta, they are not so common, but it's good to know about them. Then select which two complexities are better than all others. So constant complexity and logarithmic complexity. Then select which two complexities are worse than all others. And here is exponential complexity. I hope that everybody was able to see this power and quadratic complexity. Now the question with code. Find duplicates. It's okay for time complexity. We have n elements, and for every element, we check all other n elements to check if there are some duplicates. And this is quadratic time complexity. Now space, and here is some trick, because to provide unique elements in our result, we created set. And for example, if we have all our n elements duplicated, so we have 2 multiplied by n unique elements. In this case, our items will be n duplicates. And as we created this space, we can say that, we should say that we probably will took n elements in memory. And how many elements in memory, it depends on n. It's linearly depends on n. And that's why the space complexity here is O of n. Find duplicates. Now we again have set, but also set of unique elements. And we put it, if we put elements in unique set of elements, and if we see that they exist in unique elements, we add it to duplicates. And time complexity is linear, because here we just go through array, but here we just check if it exists in the set. And maybe I go a little bit earlier, but set is related on hash table, and to retrieve and check if there exists element is constant operation. That's why here we do n step, and for every step we do constant operation. That's why our time complexity is O of n. And as you guess, we spent space that depends on our number of elements. So we require O of n space. Yeah, I hope I will not lie. Yeah. Okay, so if you have any questions, please let me know. And our next part is about going and solve one task. I am going to put it in chat, and I think I also put my microphone to Helen because she will organize our matching in rooms.
Thank you very much, Irina. This is the end of our official presentation, so I'm stopping the recording, but we continue with breakout rooms.